Should I begin?
We'll wait. We'll wait for 2 o'clock. Then we'll start. Thank you.
Thank you.
Yes, so shall we start, Laima?
Yeah, sure.
Wait a minute. So good afternoon, everybody. I welcome you all to this afternoon session 10B, which is short papers, novel application. We'll start with the first paper titled Fusion of Deep and Non-Deep Methods for Fast Super Resolution of Satellite Images. Mr. Gaurav Kumar Naik will be presenting the same. So over to you, Gaurav.
Hi all, I'm Saksham Jain. I'll be presenting this paper titled Fusion of Deep and Non-Deep Methods for Fast Super Resolution of Satellite Images. So we'll start with the outline and the problem motivation. So the price of satellite images depends on two major factors, the most important of which is the sensor quality. So high image quality requires high sensor quality, and the prices are high because of that. And for low-cost satellite imagery, what one can do is obtain a low-resolution image and improve the image quality via super resolution. Super resolution is simply take a low-resolution image and produce an estimate of a corresponding high-resolution image. Now, super resolution is an ill-posed problem because there is no one correct answer. Multiple high-resolution images can be produced from the same low-resolution image. And so there are two categories: multiple input images and single input image. So this work is on single input image super resolution. There are two major broad categories of methods for super resolution. So one is non-deep methods, and one can be categorized as the deep methods, and both have their pros and cons. So non-deep methods such as the bicubic interpolation, the bilinear interpolation, these methods are very, very fast and computationally inexpensive, but they often result in overly smooth edges or ringing artifacts that are spurious signals when there are transitions of signals in the images. And the deep methods are very accurate. They produce good results with high perceptual clarity. But the cons are that these are computationally inexpensive, and the time taken to process large satellite images, which are in the orders of 12,000 by 12,000 pixels or 20,000 by 20,000 pixels, and even higher. So time taken to process such large images using deep methods such as the super resolution CNN, the VDSR, the EPACN, and such deep methods is very high. Now the objective of our work is to do intelligent fusion of deep and non-deep methods for the super resolution task, and we want our resulting approach to be as fast as the non-deep methods and as accurate as the deep methods. So we want a selective blend of these two in order to achieve both. So the proposed approach, the motivation for this is images, as I said, are satellite images are usually very large. And so what we can do is we can super resolve only for the salient regions. And for example, as you can see, in this large image, perhaps for an application, the airplane is important. It's a salient region, but perhaps we don't care about regions such as these. And so how do we select the salient region? So we can use regional information content. And in our particular problem, I'll go through the proposed method. So we have a low resolution image, and so we generate tiles, or we generate patches of size, for example, say S by S, and then we generate binary edge maps. And the way we choose which regions are salient and which are not is that we postulate that the important regions would have higher edge content. So the next step is to count the edge content in these binary edge maps and then sort these resulting patches in decreasing order of the number of edges contained. And then we allocate the top K patches, which have the higher number of edge content, to the deep model. And we allocate the remaining patches to a non-deep model, and we choose bicubic interpolation. So we give, so in our application we give the top K patches to the SRCNN, and we generate these high resolution patches. And similarly, we obtain high resolution patches from low resolution patches using bicubic interpolation, and then we tile them in the correct and we fuse them in the correct spatial um, structure, and then we receive an overall high resolution image in which selective super resolution has been done by either bicubic interpolation or by the deep model, which in this case is the SRCNN. Now, of course, the size of the patch and the how many of, and the top K, how many patches to pass on to the SRCNN are hyperparameters, and so we have to choose them carefully, and we'll show how we uh, got them experimentally in the next slide. But we note here that this is the first work done in the direction of selective deep super resolution on satellite and aerial imagery. And yeah, so we go on to the results next. Now, as I said, that the size of the tiles that we are generating and the how many tiles to pass on to the deep network, those are hyperparameters, and we do an ablation study for choosing the best one. So best combination. So these are our evaluative criteria. So we have PSNR, and we have SSIM, and we have MSC, and which are often taken as evaluative criteria for super resolution image tasks. And so we have plotted these against time. And this time is the inference time. And so these plots represent how many of these patches are passed to the deep network. So for example, so the first and the last depicted by blue and this maroon color respectively are for bicubic and SRCNN. And we have proposed, we pass 20% of the patches to the SRCNN, then 40% of the patches to the SRCNN, the top 20%, the top 40%, and similarly the top 60%, the top 80%. So, and we choose 60% because it always lies in the middle, and feel it's the right trade-off between performance and the inference time taken. And so once we have that 60%, we then see what the effect of the patch size is. So we have a patch size of, so as we can see, the performance kind of saturates after we have a patch size of 200 by 200. So we pick 200 by 200 as the patch size, right? And so we can see these qualitative and quantitative results. So this is a low resolution image. We partition the edge map into patches. We count the number of patches, and then we give the resulting patches to either the deep model and or to the bicubic interpolation. So here we've shown that the red patches are obtained using SRCNN and the yellow patches are obtained using bicubic. So this is an example of 60% of patches being passed to the deep model. And as you can see, the proposed model has a much lesser inference time than the SRCNN, and of course, it's higher than the bicubic interpolation because we are using the deep network as well. And it gives a performance that's very close to the SRCNN. And right. So before we come to the conclusion, we can talk about why this approach is well suited for this application. The important thing is that it does not depend, it's model agnostic, so it does not depend what deep network you choose to use it with. And in fact, it doesn't even depend what non-deep method you use to choose it with. So it's a preliminary approach based on how best to utilize the performance of both, like the performance of the deep network and the uh, how quickly it is done, and the inference time and the benefits for the inference time using the non-deep method. And so it does not depend on the SRCNN specifically. We have chosen to show it on the SRCNN, but you can choose any deep network and it will work as well. So in conclusion, the key challenge is inference time, and our approach performs selective deep super resolution and is model agnostic. And the current allocation, and of course, there's a lot of scope for future work. The current allocation of images, image patches, is based on the edge map, which is kind of a very naive indicator of regional information content, and much better indicators can be found. And in fact, we hope to work with them. And more sophisticated indicators for identifying salient and informative regions will be explored in future work. And more details can be found in our paper, which has been released on arXiv. So, and this was performed, this was supported by a research project with the with ISRO, and yeah, we acknowledge that. And thank you.
Thank you, Gaurav, for the very nice presentation. Do we have some questions for Gaurav now? Would anybody like to ask? Okay, Gaurav, so I have one question for you. You said it would not matter which deep network we are using for your, you have used SRCNN. And why do you say that? Have you tried different deep networks?
So, so the approach is simply to pass on once we have the patches that have higher regional content, and we sort those patches into what have top K patches which have higher regional content. We can pass that on to any network. So it can be thought of as a plug and play approach. Like you choose any deep network. So our approach does not depend on the choice of the deep network, right? So any approach you can choose for the deep network, and we can simply pass on the patches with the higher regional information to that deep network, and whatever is the lower regional information, which we postulate is not the region of the image, we can use bicubic interpolation to do that. And it works well intuitively because bicubic interpolation, that the problem with non-deep methods such as bicubic interpolation is that they produce a lot of rinking artifacts when there are transitions from high regions of high signal output. So those will be minimized if we don't have any edge content, right? So on edges, they produce spurious image signals, and if you don't have edges, in the non-salient region, then cubic interpolation should work as well. So it's
Thank you so much, Gaurav. Thanks a lot. So we now move on to the next paper, which is lay art, which is generating indoor layout using AR4 transformations. And request Shreya Goyal
Yeah,
to
hi.
present this. Hi, Shreya. Please, over to you.
Let me share my presentation. Are you able to see?
Yes, it is visible. If you could, yeah, fine.
Yeah. Okay. So, good afternoon, everyone. So, topic of our paper is layout, generating indoor layout using AR code transformation. So, in this presentation, I will be talking about just a second. Hello.
Yes, we can hear you.
I'm not able to scroll for some reason.
Can you check at your end?
Yeah, I'm doing that.
Maybe remove it from full screen and then try again.
Yeah, that's what I'm trying.
We can still see it in the full screen mode.
Yeah, I'm actually trying to remove it from the full screen mode. It's not happening for some reason. Oh, now it's happening. So, yeah. So I will be talking about the problem statement of our work, the motivation of the work, then how the data acquisition was done, then the framework of the proposed method and each step in the details. So I will be talking about the evaluation and the conclusion. So coming to the problem statement. So in this work, we try to capture the to generate a layout 2D layout of a indoor scene using the partial RGB images of I mean a few partial RGB images of a scene. So I'm not able to scroll again. I'm not sure what is happening.
That's okay. Maybe you can do the same thing again. Or maybe don't go into full screen and then you can present.
Yeah. The method we proposed for this this work was to capture a few partial images of an indoor scene and using a conventional mobile phone camera, and then capture then convert the partial images into a 2D map using 3D to 2D mapping. So the previous work which have been done in this uh, hello, hello.
Hello.
Yeah, there is some problem. I'm not sure why I'm not able to scroll it.
Go. Don't show the presentation in the full screen mode.
Yeah. Okay. So
Can you
yeah,
select the next slide?
yeah. So
Yeah, maybe you can present it like this.
So the motivation behind uh, behind this work is to in the conventional approaches of converting a generating a layout from RGB images. So authors have been using the panorama images or the spherical 360-degree images of indoor scenes to generate a layout, but also there have been a requirement of depth sensing hardwares from depth sensing cameras and hardwares to capture the depth of the scene. from the images, maybe RGBD images or panorama images. And another problem which has been occurring, so in case of the large scenes with occlusion, so there has been these methods have been failing when there are large spaces. So and the view is occluded with the furniture or other kind of objects. So for example, in this image, this is a large view of a lab, and the portion of the scene visible in the boxes are occluded because of the furniture. So instead of taking one single panorama image, if we take multiple partial image of the scene, it will carry more information to convert it from the to convert the convert to capture the layout of the scene. And there will be less information loss. So to for in order to do the data acquisition, we developed an app in Unity 3D using the Google's AR Core library, which uses the IMU sensors of a mobile phone and the camera, and it captures RGB image of the real world, and also the real world coordinator for each RGB image. So in the data set, we have one single RGB image for each partial scene, and along with it, we had the word coordinate for this. So this is the framework of the proposed method. So for a scene, indoor scene, we capture partial indoor scene images, and then we perform the depth estimation out of that out of those partial scenes. And for each partial scene, we perform a edge map estimation. So with the edge map, with the edge map, I mean the segmentation of each pixel into its wall and edge category. So with these two maps, the each partial scene is converted. A 3D reconstruction is done from for each partial scene, and a partial point cloud is generated. Then this point cloud is captured into projected into 2D. So now we have partial 2D point cloud for each scene, and also we have a camera trajectory available, which was captured using the inbuilt SLAM in the AR Core library. And using the AR Core transformation, now we transform each partial scene to its respective position, and then we do a regularization to the point cloud and generate a 2D layout. So first of all, depth estimation is an important aspect in case of indoor modeling, because depth carries the exact location in 3D for each pixel. So in traditional approaches, there are depth sensing hardwares, like, for example, Google Tango or Microsoft Kinect camera, which captures the depth map directly from the scene. Um, um, Also, the technique of using multiple images for the same scene, and depth estimation is done by feature matching. So these are the traditional approaches available. But in case of a common user, these traditional approaches become cumbersome, because availability that sensing hardware might not be available with a common user, and the multiple using multiple images for capturing the depth requires very high precision. So instead of that, if we can use depth if we can estimate the depth using the learning based method, which will be much easier and approachable. So for estimating the depth, we have used a pre-trained encoder and decoder architecture, and it basically has the encoder has basically based on the DenseNet 169, and decoder has one convolutional layer followed by upsampling blocks, and it has a leaky ReLU as a final layer. So these are the depth map which were estimated from few of the images in our data set. So in next step, we estimate the edge and boundary map from each partial scene. So edge and boundary map is basically classification of each wall and each pixel to their respective classes. So for this also we have used a pre-trained encoder and decoder architecture. So the encoder has 7 convolutional layer, each followed by a ReLU and Maxpool, and decoder also has 7 layers of nearest neighbor upsampling, followed by convolutional layer and one sigmoid layer. So these are the few examples of using the estimating the edge and boundary map in our data set. So after this, we perform a 3D reconstruction by mapping the RGB image we have and the depth and edge map we have. So we do a 3D reconstruction of each partial scene by generating a point cloud, and then we do a 2D projection of each point cloud and generate a partial 2D layout for each partial point cloud. So after this, we do the regularization. So for regularization, now we have a 2D point cloud for each partial scene. So for regularization, we extract the boundary points for each layout for each point cloud, and then we perform a k-means clustering and extract three means, which is M1, M2, and M3 from mean points from this partial 2D point cloud, and then we take 2 lines as M1, M2, and M2, M3. And since we are taking a Manhattan assumption in our work that every room is a cuboid or a cube, and there won't be any irregularity, so we will force one of the line to be 90 degree, so to each other. So we will rotate it till the line becomes 90 degree, and we will perform this for every partial point cloud. So now we have every point cloud regularized, and we will transform all the point clouds according to the word coordinates we have from the AR core library. And now we construct a polygon out of this, and we have n number of sides, for example S1, S2, Sn for the polygon, and then we will rotate each side to each other to have a 90-degree angle, because we are taking the Manhattan assumption. So now we have a regularized polygon P. So which is the 2D layout, which aligns with, which agrees with the real time dimension in our for our indoor scene. So this is basically the transformation using the AR code. So we can see that there is one word coordinate shown by xw, yw, and zw, and there is another coordinate system for given generated by AR code. So for transformation, we need to first rotate the AR code coordinate system to the word coordinate system so that they both align, and then we will first fix the position of the first image we captured, and accordingly we have rotational and translation information for all other partial scenes, and then we will transform all other partial scenes to their respective locations. So in the quantitative evaluation, we used two metric, the area and the aspect ratio metric. So we compared our method to 4 existing mobile application, which is Magic Plan, Tape Measure, iPhone Measure, and AR Plan 3D. So so we can see we did experiments for four indoor scenes, and here I'm showing the results for 2 of them. So we have we can see that the layout performed best in case of the classroom scene, and it is getting the least error percentage in the case of area and in case of aspect ratio. And in the meeting room scene, it is getting the least error in case of the area metric. Also, qualitatively evaluating the proposed method. So in layout, we have only the user have to only perform a four number of user interaction by clicking only 4 images of the scene, and any kind of manual intervention is not required. But in all other cases, there has to be there are requirement of a continuous scan of the entire scene, and there is a requirement of manually adding the corners or the height of the scene, which is quite error prone and cumbersome, because if there are furniture aligned with the corners of the scene, or the corners are occluded by any other furniture, then the error will be included in the dimension of the layout of the scene, and we have to add the corner from the furniture itself. Um, so um, concluding the work, so we propose a novel room layout generation method which does not require the depth or advanced camera images, and it is motivated towards capturing the layouts of the larger scene with occluded environment, in which the traditional method fails. So, since we are taking a few assumptions, for example, the Manhattan assumption, which can be released in future, and also in order to reduce the error percentage in the area and aspect ratio, sophisticated depth estimation methods can be involved. Also, this model can be extended to generate entire floor plan of the house, along with instead of generating the layout of a single room. So these are references. Thank you.
Thank you, Shreya, for your very nice talk. Do we have any questions from the participants, the audience? Okay, Shreya, I have one question for you. Although you have used a very nice, you have a very good depth estimation, do you think it will improve if you use any hardware like you said Microsoft Kinect or
Yeah, definitely it will improve if we use the hardware, but then the entire motivation of the problem will not be served, because we are targeting a common user. If we are using, because the sensing camera is not available in every mobile phone, every conventional mobile phone. So if we are targeting a common user, we should use the single RGB images instead of using any RGB-D images, or any panorama or any kind of sophisticated images. So definitely with extra hardware involvement, there will be improvement in the performance. But yeah,
Thank you so much. I agree with you.
yeah.
So we move on to the next talk now, which is procedural generation of roads with conditional generative adversarial networks. And I think Mr. Kelvin Lin will present the same. Mr. Kelvin Lin.
Hi, can you hear me?
Yeah. So over to you, Kelvin.
Can you see the slides? Hello?
Hello. Can you make it a little bigger?
Is this okay?
Fine. Yeah. Great.
Okay, then I shall begin. Hi, good afternoon. Today I'll be presenting on the procedural generation of terrain using machine learning. So in this presentation, I'll discuss why this topic was chosen, go through some existing methods, propose the framework that can be used to generate road networks, finally show some results and discuss some limitations.
Excuse me, Kelvin. Now it is fine.
Hello, is this okay?
Yes, it is fine now. Now we
Okay,
can start.
So first of all, what does procedural terrain generation refer to? Procedural generation refers to the use of algorithms to generate content with minimal human input. So terrain refers to both natural terrain, such as mountains and rivers, as well as man-made terrain, which includes roads, cities,
Excuse
and
me,
buildings. Yes?
Kelvin. We cannot see. We can see only half your presentation. Half of the part is covered.
What do you mean half of it is?
Now it is fine. Now we can see the whole thing.
Oh, okay. Hold on.
You may continue.
Can you see the whole presentation now?
Yes, it is fine now.
Okay. So terrain refers to both natural terrain, such as mountains and rivers, as well as man-made terrain, which includes roads, cities, and buildings. So procedural terrain generation thus involves the creation of terrain using algorithms, as opposed to having a human handcraft the entire terrain by hand. So terrain in earlier games was almost entirely modeled by hand, which took a very long process. In recent times, procedural terrain generation has seen use in games such as Minecraft and Spore, where the biomes and landscaping are designed using random seeds. This saves a lot of work in the development process and allows the user to experience different types of gameplay, as the content is almost always different with a different initial seed. This brings us to the scope of our project. So road networks are often a very important part of gameplay. In games such as Grand Theft Auto, the game takes place mainly within the city, and so the road network directly influences the gameplay, navigation, and pathfinding. Missions in such games involve traveling from one point to another with constraints such as the time limit. In games such as Players Unknown's Battleground, the road networks allow for vehicles to travel safely. Players thus make use of their knowledge of the road network to carry out strategies such as ambushing other players by making use of choke points. The road network here thus affects player strategy and behavior, as there may be more players around roads. However, present methods of road generation do not often have much control over the output process. The user might have a certain set of roads in mind already, and may just want to add some new roads in addition, or may want to model a city in the style of a particular region. Present techniques do not function very well in this regard, which will be discussed. Present PTG techniques can be classified as traditional, example-based, or that make use of machine learning in some ways. Since a road can be interpreted as a line connecting two points together, modeling road generation as a graph problem is very common in traditional PTG algorithms. Some algorithms thus make use of shortest path algorithm in the creation of new road networks from one point to another by considering costs such as the presence of water or height differences. Other algorithms include recursive subdivision, where the road network is created over a region by repeatedly dividing the region into two parts until an area is too small to divide further. Lindenmayer systems have also been used to generate roads. Now, one common issue with such algorithms is that the roads are almost very predictable, and the general appearance is quite similar. While grid-like cities, such as the one on the right, are similar in style to those in certain countries, such as America, games that involve heavy use of road networks, such as Grand Theft Auto, may not find these too suitable, as the player may find it too repetitive and predictable for gameplay purposes. There is also not much control over the output, as it is often generated randomly. Example-based algorithms make use of some existing data to generate new data. Two common approaches for example-based road generation include patch-based and growth-based algorithms. Like its name suggests, patch-based algorithms apply and transform patches from a prefab list, which are then applied to create new roads. On the other hand, growth-based algorithms take in an existing road network and grows the secondary roads by simulating traffic and direct propagation. Example-based algorithms tend to generate road networks that are less rigid and grid-like, and generally have a higher level of control over standard algorithms because the user can change the road patches that are used for generation. However, this will require the user to be familiar with how the algorithm works, and will also require them to provide their own patches if they want to make their own style of roads. A lack of knowledge or variety in such road patches will lead to poor results, such as having multiple roundabouts in close proximity. Generative adversarial networks are networks that consist of a discriminator and generator network. The discriminator network takes in an input from the generator network and judges if it is realistic enough, assigning an accuracy score. In standard GANs, the generator network takes in random noise and generates an output which is fed to the discriminator. The generator aims to get a high score from the discriminator, while the discriminator aims to assign a low score to the generator's output, thus making these networks adversarial to each other. The discriminator learns to judge samples more accurately, while the generator learns to create more realistic samples, and eventually stabilizes at a point where the discriminator is unsure about any given input, giving a 50% accuracy score to any provided input. The uses of GANs has been explored in some recent papers, with one using GANs to generate the landscape terrain and making use of the Earth Explorer data in generating the terrain height maps. Street GAN is a GAN that is trained to output road networks. While street GAN was trained on a standard GAN, it has low controllability like other standard algorithms because the user can only affect the output by giving it different noise samples. While not related to PTG, the pix-to-pix algorithm is a conditional GAN that learns how to translate an image into another image. Pix-to-pix was used to perform tasks such as coloring or generating colored handbag pictures from an initial user sketch. And this algorithm forms the basis of our approach. Our proposed roadmap generation framework is as follows. In a training phase, OpenStreetMap data is pre-processed, and the data is used to train a conditional GAN. This CGAN learns how to translate a given base map tile into a map tile that contains secondary roads. In the usage phase, a user makes use of graphical user interface to make their own sketches. The sketch is then fed into the trained CGAN, which gives an output containing secondary roads. It can then be further processed for usage in game engines such as Unreal Engine 4. Our framework makes use of OpenStreetMap tiles as the database. OpenStreetMap data was chosen because it is based on reality, making the generated output likely to be more accurate. It's easily available for download, making training on a real region easy, and is highly customizable through the careful use of rule sets and style sheets. This customizability allows us to train CGAN to generate not just secondary roads, but other features such as railway lines as well. During the pre-processing step, we take each tile and apply two different rule sets to it. The first rule set only causes primary roads to be rendered. The secondary rule set causes primary, secondary, and building locations to be rendered. These two rendered tiles thus form a single training instance, where the left tile with only primary roads forms the input base tile, and the right tile is a target output for this particular base tile. This is the architecture for our discriminator network, which takes in a base tile as well as an output tile which can be generated from the generated network or from our training data. The inputs are concatenated and fed through convolutional layers, and finally a score representing how realistic the output tile was with respect to the base tile is returned. Each convolutional block contains a convolutional layer of window size 4, max pooling, and a leaky value as an activator function. In the second layer and beyond, we also carry out batch normalization to improve the learning speed. This is the architecture for our generator network, which takes in a base tile and outputs another generated tile. During the training phase, this is used to train the discriminator, and during the usage phase, we will use this generated network to take in the user's sketches and generate what the user wants. The generator network is adopted from the pix-to-pix algorithm from Isola et al.'s work and makes use of an encoder-decoder network with skip connections. Each encoder block contains of a convolutional layer and a leaky value activation function. The encoder blocks encode the base tiles information, which is then decoded by the decoder blocks, which consist of upsampling layers. Skip connections are used here, where successive layers of encoder-decoder blocks are connected. The output of the encoder block is also concatenated to input to a decoder block as shown. We also use skip connections so as to improve the learning of the model by minimizing the vanishing gradient problem. Here is our training methodology. We train the conditional GAN for a total of 5,000 cycles and evaluate the performance every 100 cycles. So during each cycle, we select a random batch of base tiles as well as the corresponding target tiles, which are fed into the generated network, which yields the generated tiles. We train the discriminator with the real target tiles with a target score of 1, and train the discriminator with the fake generated tiles with a target score of 0. Finally, the output scores on the discriminator network are used to update the generator network as well part of its loss function. We also implement a graphic user interface for the user, which consists of two canvases, and the user draws on the initial primary road network on the left canvas using their mouse. Once they're satisfied, they can press the generate button to generate the result, which is shown on the right canvas, and if they are satisfied, they can save the image or further process it for use in Unreal Engine 4. During the post-processing step, the image colors are read and split into their respective layers. So for our initial rule set, with the different colorings from our initial rule set, we can generate 3 different layers that consist of the primary road networks, the secondary road networks, as well as the buildings. These subtiles are in grayscale and can be used directly in Unreal Engine 4 landscape creation to paint the terrain. As seen here, this landscape was made in Unreal Engine 4 using subtiles created in such a manner. So here are some of our results. After training the CGAN, we tested it on our test data and find that the output tiles are generally quite similar to the ground truth, although there tends to be some noise in the output which causes the image to be blurry. We also test the GUI by letting users draw on the GUI canvas. So here is an example of a road that is used. And here is the output generated with this initial road network. However, there are noise artifacts present which causes it to be blurry at times. To show that the generated terrain can be used for game development, I used the landscape generated in Unreal Engine 4. So as proof of concept, I only carried out minimal work on the terrain and only added in foliage using Unreal Engine 4's foliage painter and added in some simple houses built using a cube and a pyramid in the locations designated as building spots. And from here, created a simple driving simulator using this generated terrain. Comparing our framework to existing work, from the left image, we can see a growth-based algorithm which was chosen due to the similar goal of allowing users to draw an initial road network. The middle image is from StreetGAN, which was chosen as the user scans as well as having a similar dataset of OpenStreetMap. Our algorithm is able to generate roads specific to the given input tile, whereas StreetGAN does not have the same customizability and can only generate tiles completely based on noise. On the other hand, the growth-based algorithm is able to generate roads and bridges and also takes in water body presence into account. Some of our limitations include the inability to handle elevation and water bodies, which can be trained on in the future. While water bodies can be rendered into tiles through rule sets, the rendering of water bodies itself often involves elevation, and this will be much more complex to carry out in game engines such as Unreal Engine 4. OpenStreetMap tiles also do not have information on elevation, which means that the CGAN cannot be trained to take elevation into account. In addition, the tiles will only tell you where the buildings should be placed, but it does not actually tell you how the buildings should be placed, as the tiles only tells you the general shape of the building. In conclusion, using a CGAN, we have developed a framework which can be used to generate rope networks for game development. This CGAN can be trained on different regions to create networks with different styles. Some future work can involving satellite images, which can be used to handle elevation data better, as opposed to our current approach of using OpenStreetMap data, which is entirely a two-dimensional data. 3D building algorithms can also be used to remove the step of manually adding buildings. But however, this will require much more data set of rendered 3D model buildings and will be much more difficult to carry out. This brings us to the end of our presentation.
Thank you, Kelvin, for your very nice talk. I would like to ask if anybody has a question from the audience. Okay, if nobody has a question, I would like to ask you a question, Kelvin. So
Yes.
I wanted to know whether when you generate the roads, does the width of the road also come into play?
I'm sorry?
How broad the road will be?
The what of the roads?
The width, how broad the road will be.
Yes. This road will be affected by how the user draws. So if the user paints the roads with if the user wants to draw like a longer road, they can just draw longer. And if they want to draw a thicker road, they can just manually make the roads thicker by drawing repeatedly.
Thank you, Kelvin. Thanks a lot for your presentation. We now move on to the last presentation in the session, which is text to clip art using attention GAN. And Mr. Toshihiko Yamasaki will be presenting the same. I hand over to you, Mr. Toshihiko.
Can you hear me?
Yeah.
Okay, so let's start our presentation. Our research topic is text to clip art using Attention. And we do this. Oh, sorry.
I'm sorry, I think Mr. Yusuke Kondo is presenting, right?
Yeah, yes.
Yeah. Okay, thank you. Over to you, Yusuke.
Okay. Our research topic is text to clip art using Attention, and we do this study in third year undergraduate and for student experiment. So in recent years, many researchers and research institutions are making effort to improve generative models. One of the hot topics in generative model is text-to-image generation task. In text-to-image generation task, given a sentence describing describing situation scene, the model synthesizes corresponding images. Most of them are a type of GAN application. That kind of studies are trying to generate high-quality, natural, and photorealistic images. However, there are only a few studies for creating illustration, especially for clip arts from text. The purpose of this study is to build a text-to-image generation model, especially for clip arts. Our model takes scene describing text as input and output corresponding clip arts illustration. We aim to empower ordinary users who are unable to find or do appropriate illustration or clip arts that conveys their ideas properly. Okay, now we are going to talk about training acceleration. First, we tell you about Attention. Most of text-to-image generation models using GAN embed the whole input text into a single vector and use it as input for the image generation neural network. So these models face a number of problems. One of the problems is that the detailed information of an input sentence, that is, the fine-grained information at the raw level, gets lost in the conversion process. This characteristic prevents the generation model from making high-quality detailed image. Attention is a model that solves that problem. Attention is the most unique and significant aspect of Attention. It prevents raw-level information from dropping out in the vectorization process and enables the generation model to create clear and precise pictures which reflect the raw-level meaning of the input text. Attention has two different training stages. First, a deep attentional multimodal similarity model, DAM-SM, is trained using pairs of strings and image in the dataset. The DAM-SM takes raw features extracted from the text by text encoder and the local image features extracted from the generated image by the image encoder as input. Subsequently, the attentional generative network is trained. The trained DAM-SM is used as a part of the objective function to penalize the attention training. Second, image encoder using GAN trains the way of making appropriate image from sentences. In GAN training, features at different granularities from the sentence level to the raw level are injected in the middle of the training process. This time, we approached DAM training stage and changed image encoder from Inception v3 to VGG16. This change has reduced the DAM-SM learning time by half. Let's illustrate this with a figure. This is the architecture of Attention, and we have downsized this image encoder to accelerate DAM-SM training. Next, we talk about the change of image encoder. We change image encoder from Inception v3 to VGG16. This is because despite the larger number of parameters than Inception v3, VGG16 has a shorter training time due to its simpler architecture. We will explain in detail why VGG16 has a faster learning time. Inception V3 has a module called the Inception module that does calculation on multiple convolutional layers in parallel and connects the results to each of the layers. Inception V3 has a module and is formed by connecting many of these inception modules. Consequently, inception V3 learns by repeating data division and integration, which is a complicated learning process. It makes the original image encoder using inception V3 huge and complicated, requiring long training times. This is one of the main reasons why it is difficult to adapt Attengan to the corresponding domain. In contrast, VGG16 has much more parameters than Inception V3, but has much simpler architecture than Inception V3. Therefore, the complicated process of dividing tensor, learning in parallel, and integrating tensor is not necessary, as is the case in Inception V3. Compared to Inception V3, VGG16 makes it possible to learn sufficiently with minimal computational costs and easily adapt to clip art. In summary, changing image encoder from Inception V3 to VGG16 reduced the AMSM training costs. This time, in accordance with the change of image encoder, we changed output of image encoder. Specifically, image encoder output is changed from 17 times 17 times 512 tensor and 512 tensor to 14 times 14 times 512 tensor and 512 tensor. The local image features use a 14 times 14 times 512 tensor immediately before passing the pooling layer, though the fully connected VGG16 layer. Additionally, the 496 dimension vector corresponding to the second layer of the fully connected VGG16 layer is extracted and converted to 512-dimensional vector by the one-stage fully connected layer used as a global feature of the image. A 14 times 14 times 512 tensor is adopted as a local image feature after passing through the 13th convolutional layer of VGG16. Similarly, the global feature is obtained through the second fully connected layer, transforming the 4096 dimensional vector into a 512 dimensional one. The DAMSM use both. So next, we will tell you about the dataset we used. We collect illustrations and corresponding scene description text from Illustrator. Illustrator is Japanese, so free to use illustration archive service and have over 20,000 clippers. There are two advantages to use Illustrator. Firstly, so all of the Illustrator's picture illustration is drawn by only one person, Takashi Mifune, and sharing the same style of painting. This is very good for running for the model. And secondly, so the description is so detailed and objective. For example, as you can see in the right side of the slide, you can see an illustration of a researcher in a white coat scratching his hair for lack of a badge for experiments. And so this very detailed description is good for Attengan model to run text-to-image synthesis. And we built a text-to-clipper generative model, especially for Illustrator dataset. And we did web scraping and gathered about 15,000 pairs of text and image for training. And text is written in Japanese, and we did word separation through morphological analysis engine in Janome, a pure Python and Japanese morphological analysis engine. And image is original image has different size, and we compressed from different original size to this this size. Yeah. So next, we will tell you about training condition. So we used one NVIDIA Tesla V100 GPU, and we did training for 490 epochs for DA-MSM firstly. And secondly, we did training for Attengan module for 110 times, for 10 epochs. And so the main improvement of our modified Attengan module is, as you can see in the table. So the training time of DA-MSM is reduced about a half, as you can see in the table. And totally DA-MSM training time is shortened from 88 hours to 40 hours for this Illustrator dataset. So we can visualize what DA-MSM learned by attention. So the image in the slide is an illustration of a man who eats rice with chopsticks, and so you can see the word index over Japanese text, and word index 0 corresponds to chopsticks, and word index 2 is correspond to rice. And we visualize DA-MSM attention with in this image. You can see that the DA-MSM model clearly learned what chopsticks and what rice is. In this slide, you can see the result from trained text-to-clipart model, input text and output corresponding illustrations. Each input text has two illustrations. Left one is pure Attengan model using Inception v3 as image encoder. Right one is our proposed method, modified Attengan model, DA-MSM model using VGZ16 as image encoder. A modified Attengan model, DA-MSM model, it takes less training time, as we mentioned before, a half, but the quality of output image is not so different. And as a rule, generating a human illustration worked especially well. However, as is often the case with generative model, some output illustrations were not acceptable. For example, when we generated an image of a strawberry, the image did not seem to capture the characteristic of strawberry, except for its color. The right one, an illustration of curry, you can find something like a human head in curry, and this is not good generative result. There are two main problems we hypothesize. Firstly, a non-human illustration is insufficient in dataset. Over 85% of images are human illustration in this dataset, and the data for non-human illustration is not enough for the text-to-clipart model to run good data distribution for generative model. Secondly, the model is not good at dealing with short descriptions. The baseline experiment, Attengan paper, used more rich expression like So it can take this set. So the bird has a yellow color and blah blah blah. So the example in this slide is to show description as input for the model, and that's why so an image of a strawberry and image of curry did not work well. So and maybe Attention architecture is not suited for generating image from short text. So in conclusion, in this study, we built a dataset of clip art from Illustrator and built a text-to-clip art generative model. And the baseline model, Attention, is a total text-to-image generation model, but require high computational resources and long training time. And our contribution is we reduce training time of Attention by changing image encoder, not changing quality so much. So that's all for our presentation. Thank you for your listening.
Thank you, Mr. Yusuke, for your very informative presentation. And I would like to ask the audience if anybody has any questions. Okay, so Yusuke-san, may I ask you a question?
Yes.
My question is that in which part of the text to clip art is the most challenging part according to you?
The most challenging part, to say the truth, it is very difficult for us to build a data set. So yeah, that's the most difficult struggling part of our experiment.
First building the Thank you so much. Thank you to all the speakers for the very nice session.
Sorry, ma'am. Sorry to disturb you. Actually, we have a question from the audience.
Yes, I cannot see the questions.
Yeah, I would just allow her to put on her mic. Just give me a second.
Yes.
Hello.
Hello.
Hi, Yusuke. Thanks for your presentation. I just wanted to understand what data set you have used, and could you please repeat that if in case I've missed? And also, what are the kind of labels there? So, if there is, let's say, an image, is the label the entire description, or does it have the labels of the individual objects that are present within the image?
Thank you for your question. However, could you say again your question more slowly? Sorry.
No problem. I wanted to ask, can you repeat what data set you have used?
Okay. So we use Illustrator. Illustrator is web archive for illustration, and however, Illustrator has only Japanese description for each image, and you have to you have to do web scraping for yourself.
Okay. And the labels are as is shown here, is it? It's the entire description is the label for each image?
Yes.
Okay. Okay, is it open sourced?
It's if you do not use for commercial use, you can use as much as
Okay.
however, you should pay attention about the description in the site. So you should check by your own in this URL.
Okay. Thanks, Yusuke.
Okay, thank you for question.
Any other questions? So I would like to thank all the speakers of the session and all the audience and the participants. Thank you so much for making this session a successful one. Thanks a lot.
Thank you, ma'am.
Most welcome. Thank you. So I think the session is over now.